This video is for section 13.4 about changes of state. The learning goal is to understand the use of a phase diagram. Let's discuss that learning goal. When a substance changes its state, this is called a phase change. Phase changes include the following processes. Melting is when a solid changes to a liquid. Freezing is when a liquid changes to a solid. Vaporization is when a liquid changes to gas. Condensation is when a gas changes to a liquid. Sublimation is when a solid changes to a gas. And deposition is when a gas changes to a solid. Notice how these come in pairs. These are together, and these are together. The temperature at which a given substance undergoes a phase change depends on the forces of attraction between particles of the substance and upon the external pressure on the substance. Conversely, the pressure at which a given substance undergoes a phase change is influenced by the temperature of the substance, that is, how much kinetic energy its particles possess. A phase diagram is a diagram that shows the conditions of temperature and pressure at which a given substance exists in its different phases. Here is an example phase diagram. This one is for the substance water. Along the horizontal axis is temperature, being measured in degrees Celsius. The spot right here is where 0 degrees Celsius, the spot right here is 100, and so on. On the vertical axis is pressure, measured in kilopascals. This mark right here is 101 kilopascals. This up here is 22,000. You'll notice some heavy dark lines that separate this quadrant into regions of space. There's a dark line down here, and it comes up with a slight curve to it to point B, and then a heavy line runs upward in this direction, and another line which has a slight curve to it is running off in this direction to point C. These dark lines separate this quadrant into 3 regions of space. The blue shaded region is where water is in solid form, and that's called ice. The violet shaded region is where water is in liquid form, and the tan region is where water is in its gas form, and that's called water vapor. This phase diagram shows the conditions of temperature and pressure at which water exists in these different phases. For example, when the temperature of water is 100 degrees, you would go over on the x-axis to where 100 is, and then pair that with a particular pressure. Let's say 90 kPa. So straight above the 100, you would go up until you reach a height of 90. I think that's about right there. If this number is 101, then this could be about 90 right there. This dot, located at a temperature of 100 Celsius and a pressure of 90 kPa, is in the tan region, which means water is a gas at 100 degrees Celsius and 90 kilopascals of pressure. Let's locate another point on this phase diagram. Let's say that the temperature of water is 50 degrees Celsius. If this is 0 and this is 100, then 50 is halfway in between. Let's also say that the pressure on that water is 105 kilopascals. So I'm going to go straight up above the 50 until I reach a height of 105. And that's approximately right there. Because if that marks 101, then this one a little bit higher might be 105. This dot indicates that water is in liquid form at the temperature of 50 degrees Celsius and the pressure of 105 kilopascals. The heavy dark lines that separate the phase diagram into the 3 different regions are called equilibrium lines. They are the boundary lines between the regions that show the conditions of temperature and pressure for which the substance is in equilibrium between 2 phases. Let's look at the phase diagram again. And this time, pick a point that's actually on one of those boundary lines. For example, this point right here. This dot is for 0 degrees Celsius and 101 kilopascals. At that combination of temperature and pressure, water is in equilibrium between its solid and liquid phase. Solid water is melting into liquid water at the same rate that liquid water is freezing into solid water. Another vocabulary word having to do with the phase diagram is triple point. The triple point shows the condition of temperature and pressure for which the substance is in equilibrium between all three phases. Let's take a look at the diagram for water again. Can you find the triple point? It's this dot right here, which has the letter B next to it. At the temperature of 0.01 Celsius and a pressure of 0.6 kilopascals, water is in equilibrium between all three of its states. Another vocabulary word is critical point. Beyond the critical point, a substance cannot be in equilibrium between the gas and liquid states. Let's take a look at our diagram for water. Do you see where there is a critical point? It's point C. It's the end point of this dark boundary line. The line doesn't extend upwards forever. It actually stops at that dot. If the temperature of water is higher than 374 degrees Celsius, or if the pressure upon the water is higher than 22,089 kilopascals, then there cannot be an equilibrium between the solid and liquid phases of water. The phase diagram that we were looking at is for water. It shows temperatures and pressures at which water exists in its different phases. Scientists have phase diagrams for other substances as well, and they created those phase diagrams from experimenting with other substances. For example, here's another substance, alcohol. If a scientist was interested in at what temperature and pressure alcohol could freeze into a solid, he could do experiments and then create a phase diagram for other people to use to see those temperatures and pressures. Here are some check for understanding questions, and these questions refer to the phase diagram for water, which is in these notes, but it's also on page 438 of the textbook. I'll pause the video for you to answer these, and then we'll discuss them. Number 1, in which state is water when the temperature is 50 degrees Celsius and the pressure is 101 kilopascals? Water would be a liquid. Number 2, in which state is water when the temperature is 50 degrees Celsius and the pressure is 0.6 kilopascals? It's a gas. Number 3, the equilibrium line connecting point B and C in the diagram on the previous page shows the boiling point of water for various pressures between 0.6 and 22,000 kPa. That's true. That line is in between the gas and the liquid phase. When you choose dots on that line and look down to the x-axis to read off the temperature, those would be boiling point temperatures, the temperature at which water changes from liquid to gas. Number 4, the melting point of water when the pressure is 101 kPa is 0 degrees Celsius. And number 5, explain how you could force water to be in liquid form even when the temperature is 105 Celsius. Remember, normally water boils at 100 Celsius. Well, how can you make it so water doesn't boil so that it stays in liquid form? You could increase the pressure to a value greater than about 110 kPa. Now, this value right here I'm guessing at because our phase diagram isn't that accurate. It doesn't have a lot of marks on the x-axis and y-axis. So we have to guess at where 105 Celsius is, and then what would be the pressure at that point. This concludes the lesson about using phase diagrams to tell when a substance exists in the gas, liquid, or solid phases.